Dear friends, we want to learn here some basic concepts in regard with the rope transport. You know there are many types of ropeways: surface lifts, aerial lifts with chairs or gondolas, fixed or detachable, monocable or bicable. We cannot treat all of them. We will display only one type here, that is the bicable up and down aerial ropeway, similar to the one in the picture, with the purpose to show the physical behavior. As done also for similar videos, we will use a very simplified model in order to compare the theory with experimental data. Let's see together.
Let's start with the definition of the problem, and soon after we switch to the physical model describing it. From the model we simulate one load condition and we get some results. Then we start the experimental phase to check those results. The first trial repeats some load conditions of the simulation, while the second trial makes a different one. Eventually, the second condition is also simulated in the model to validate it. Finally, we speak about difference between the model and the reality, giving some hints about how cars and ropes are built. Before speaking about any problem definition, we need to understand how such a ropeway is built. That we will see in the next slide more in detail. But now let's consider some definitions. From now on, we call carriage the vehicle or car that must be transported via ropeway. We have said that there are two cables. One is the carrying or truck cable, and the other is the hauling cable. The supports of the ropes we call trestles. Somebody says also towers. Our task is to find, for any position of the carriage, the load at the hauling rope and its displacement. To make it simple, we make some assumptions. There is only one carriage between two trestles at a time. This is actually the case of up and down ropeways. We neglect the rope's weight with respect to the weight of the carriage. And there is no friction. The method is based on a two-dimensional geometry with punctual mass. The calculation is repeated for different carrying rope preloads. We will see this concept afterwards. Eventually, the theory is compared with the trials. A ropeway bicable is made of two independent cable systems. The carrying ropes are minimum two, one for each side. Each cable is fixed at one station and loaded with a counterweight at the other station, like in the picture. The hauling rope is endless and driven by one motor plus reducer and wheel at one station, returned at the other station by a free wheel. The trestles support both the carrying and the hauling rope. The carriages move opposite at each side of the cableway. When one raises, the other lowers. Their motion is simultaneous since they have the hauling rope in common. Moreover, there is a third rope system, also endless, that is the rescue rope. This rope is used to access the carriages in case of emergency, but is not represented in the sketch, because not significant for our scope. The load at the carrying cable capital T is given, is a preset due to the counterweight. The load at the hauling cable capital F must be found, apart from the preload, and the carriage displacement F also must be found. This is the displacement of the carriage referred to the segment AB that connects the trestle at a higher elevation with the trestle at the lower elevation. The delta elevation we call h. Moreover, we call capital L the distance between A and B. Capital P is the load of the carriage plus the payload. And capital T, as we have said before, is the load of the counterweight that we assume being the preload of the carrying rope. We observe that this load is constant. and does not change after and before the carriage. Moreover, we call capital L1 the distance between capital A and capital P, and capital L2 the distance between capital P and capital B. The horizontal and vertical components of capital L1 we call X1 and H1 respectively, and the same we do for the components of capital L2. They are X2 and H2. Finally, we introduce three angles. Phi is the inclination of the segment capital L, alpha is the inclination of capital L1, and beta the inclination of capital L2. With the help of geometrical considerations and force balance, we will solve our problem for any given horizontal position. A horizontal position of the carriage is given by the coordinate x1 or x2. We remember that the horizontal distance is known. The angle phi is calculated as the inverse tangent of h over the sum of x1 and x2. By writing the sum of the moments with respect to the point capital A, we get this expression. Capital P into x1 equals capital T times capital L times sinus of phi plus beta. And from this equation we get beta as displayed. From beta we can find the coordinate h2, and from h2 we find h1 and eventually the angle alpha. Now we write the sum of the moments with respect to the point B. We need just to solve this equation for capital F, and we are true, while L2 is the square root of x2 square plus h2 square. The vertical displacement of the load with respect to the segment AB, that is F, is given by this expression. We have to repeat the procedure for any other position of the load capital P. If we assume that the preload capital T is 400 Newton, the load capital P is 240 Newton, h, the delta elevation, 1.3 meters, and x, the horizontal distance of the supports, 13 meters, that is also the sum of x1 and x2, we find the values displayed in the table at the right side. In the chart we represent in orange the vertical displacement of the rope H1 and the corresponding hauling force capital F for any position x1 of the load. The displacement F with respect to the segment AB we find also in the table aside. In this slide, we have represented the physical model with the program GeoGebra. This program allows to visualize the motion of the rope while the load is racing from B to C. We have called C the point A in this visualization. Beside the displacement, there are also the forces on the carrying rope T1 and T2. They are equal and constant in modulus, but the inclination is changing. The hauling force is not represented, however, it is the one that makes the sum of the forces equal to 0. In the video comments, you can find a link to the GeoGebra file and play with all the parameters. Enjoy yourself! Let's start now the experimental phase. In the first experiment, we are reproducing the physical model described before. For doing that, we need a carrying rope suspended between two supports, a hauling rope, two water canisters, and a couple of instruments, a laser meter and a dynamometer. The big canister we use as a counterweight for tensioning the carrying rope via a pulley in proximity to the higher support. The second canister simulates the carriage, suspended by another pulley over the carrying rope. The hauling rope is fixed to the carriage, returned through a pulley in proximity to the higher support and maneuvered by an operator. Between the load and the hauling rope, a dynamometer meters the force. Let's see the video aside. The experiment results are above. At a distance of 0.5 meters from the higher trestle, the metered hauling force is 77 Newton, while the theoretical one should be 82. At a distance of 4.1 meters, they are 47 and 49 Newton, respectively. In the second experiment, we increase the preload of the carrying rope to 600 Newton. The other parameters stay the same. The hauling force metered at a distance of 0.5 meter from the higher trestle is 64 Newton. Moreover, we want to meter the maximum displacement versus the floor, H1, that turns into 2.18 meter. We could not meter the maximum displacement in the previous experiment because the canister touched the ground. Now we repeat the theoretical calculation for the new conditions, and we find the values displayed in the table at the right side. From the chart, we take the values corresponding to the experiment and we compare them. The forces at a position x1 0.5 meter are very close each other. The maximum displacement given by the theory is actually something lower. The chart is also hereby represented. We will examine the reason for deviations in the next slide. Some general observations. Why there are deviations between theory and experiment? About displacement, the supports are not perfectly stiff. Actually, the right one in our experiment is a wooden post and can swing a little bit. Therefore, we found a greater displacement in the reality. About the forces, it is difficult to read the dynamometer values in real time. We remember that our model is a simplified one, as said at slide number 3. The performance of a real ropeway should take into consideration the dynamic behavior, not just a static one, the simultaneous motion of two cars running together in opposite directions, and the preload of the hauling rope. That rope is shared among the two cars and it is also preloaded, but this we have neglected in our simulation and also in the experiments. Last but not least, in reality the car is suspended by a shoe made by many rolls, not just one, and that makes the geometry more complicated. Here we can see a 3D model of a 3-ropes car. 2 ropes are for carrying and 1 rope for hauling. The considerations we have seen up front are the same. On the right side there are typical sections of hauling and carrying ropes. The carrying rope must have a closed and smooth surface because the car has to roll on top of it. Typical diameters of a hauling rope is 25-30 mm and for a carrying rope 50-60 mm. Please see the credits in the video comments.
I hope you have enjoyed this presentation. I'm always happy to know your opinion, your comments, and see you next time. Bye bye.